Hey everybody, how's it going? Today we have an A1466 Macbook Air. This appears to not be turning on. We can open this up and see if we can figure out what's wrong with it and make it work again. I invite you all to watch as I embark on this process, so that you may learn, but you also may assist me if I get stuck. I'm counting on you. So we're going to take the case off of this device. Are you excited? I'm excited. So what we're going to do over here is we're going to unplug the battery. I want to see how many amps the board is taking. Not how much it's taking to charge the battery. Soon, soon. I have a lot on my plate. Okay, we don't even have a green light, and we have 0 amps being taken. I see you, Sarasso. And Enzik Shatria is here. Okay, so we are going to take the screws out so that we can take the board out and have a look at it. You always want to give the board a look. Now, does anybody who's watching here know the first power rail that needs to be present in order for us to have a green light in the charger? And why we would need that power rail present in order for us to have a green light in the charger? Looks like Corey's been paying attention. Corey must have read the document that's linked in the description of this video that describes how everything works, which is available for free for anybody who wants to click it. No trials, no pay for the rest of it to be unlocked, completely free educational documentation right in the description of this video. That's right, folks. PP3V42_G3hot is the first rail. The first reason that rail has to be present first is because that's what powers the system management controller, which speaks to the charger on the one-wire line. That's what the middle pin of this charger is for. For the one-wire circuit, it speaks to the charger and tells it, I'm a MacBook. I'm a good MacBook. Turn on. The second reason PP3V42_G3hot is the first rail that needs to be present is because that's what actually powers the one-wire circuit, which is going to allow the charger to speak to the system management controller, which is located on the DCN board. As always, I'm going to unplug the SSD. There's no need for the SSD to be plugged in while we're working on this computer. In case anything goes wrong with the repair, we can always replace their machine, but we can't replace their data. There are many simps out there. Simps so strong that I might just call them Homer. Because they a simp, son. That would say that if someone does not have their data backed up, they deserve to lose it. Makes me want to just walk over to their device and erase it right now. Prove a point. Yes, there are many simps out there. And you must slay them. Slay them all with your PP bus and your Amtech Flux. So now that it's out of the case, I want to see if the behavior changes at all from where it was when everything was plugged inside the case. It's possible that there was a liquid damage component plugged in that was keeping it from working properly. And that doesn't appear to be the case because it's still taking 0 amps when we have nothing on the fan. Knowing that PP3V42_G3hot is the first power rail that needs to be present in order for this to turn on, let's take a look and see where that shows up on the board using Paul Daniels' software. Paul Daniels' software is available at pldaniels.com and makes a lot of what we do here so much easier. PP. Look at that. It shows me everywhere on the board that it's present. Now, to save time, I tend to want to find the biggest point on the board that is present. And here, it's this inductor. It's pretty big. So what we're going to do is we're going to see if PP3V42 is present on this part of the board. Also, we're always looking to do numerous things at once. It's always important to be doing multiple things at the same time. And one thing that I see over here is evidence that liquid got on this computer at one point in time. Can you see it? See this? This is some like crusty stuff. It's kind of like food or, I don't know, a bit from an Oreo milkshake or something like that. We're always paying attention. You're never just doing one thing at a time. You want to be looking at the entire landscape. You do have peripheral vision when you're measuring something. So it looks like our PP3V42 is only 2.4 volts. Let's go over a common thing that can happen that can cause that. Behind door number 1, you can have a short to ground, which is going to bring your power rail down. Behind door number 2, the feedback going to that chip is not proper, so it thinks that it needs to lower the amount of voltage it's creating. So let's take a look at how the PP3V42_G3 hot power supply works on the schematic over here. This is the schematic, and this is where PP3V42_G3 hot is created. Now, as you can see, this chip is going to take either 8 volts from the battery, PP bus G3 hot, or 18 volts from the charger, PP18V5 DC in, and it's going to take that, it's going to turn it into 3.42 volts out. Now, once the chip's done doing its thing and turning that 18 volts into 3.42 volts out, this chip kind of acts like a buck converter, what's going to happen is it wants to see what it's creating. So you have a little feedback network here, which is a voltage divider. This takes whatever it's going on output, and it makes it lower. That's what this voltage divider is doing. You have a resistor between a power line and then here in ground. This is going to be lower than that. Now, if the bottom resistor is missing, then this voltage will be too high. If it thinks that the voltage that it's creating is higher than it should be, then it's going to output less. I'm going to take a guess that R7096 is corroded or missing from this motherboard, or that we have a short to ground on the output of PP3V42. How do we determine which one is the case? Well, let's change our multimeter into ohms mode and find out. So the multimeter is now in ohms mode. We're going to see if we have a short to ground on output. 3.9 kiloohms. I don't know if that's right, but I'm not going to call that a short just yet. Next up, I'm going to see if that resistor is missing in that area. I honestly hope it is, because if it isn't, then this one's going to be a tough one. Now, if we were to click on using Paul Daniels' software, what we can do is we can right-click R7096, and you'll see right here, R7096. So now we take a look in the microscope. We just got to compare what we saw on the screen with what we see here. Now, this area is hairy, but it being hairy does not necessarily mean that that is the reason it is not working. A little bit of hair can actually be good for the board. It's kind of like growing a beard. This is going to be a confusing one. So now I also want to see how my input is. I want to see if my input is what it should be. So if I have 18 volts coming in over here, then everything's good. If I have 1 or 2 volts coming in over here, then there's something wrong. I'm going to check right around here on pin 6 of the chip to see what's going on there. So let's go back over to my board view, and pin 6 on input. I can measure that either on this large cap or on this pin of this diode. And that's precisely what I'm going to do. Plug in my DC in board, wiggle it around, make sure it's working. Okay. What do we have over here? 17.8. Close enough. What do we have over here? 17.8. Close enough. Yet output is 2.4. That's a troll. That's a giant troll. I wonder if R7096 is actually working or if it's blown. I'm going to unplug power so that I can use ohms mode to find out. No, that's probably going to be exactly what it's supposed to be. Daniel, that is hair. Hair of the troll. Okay, let's go on a journey around this board. See if anything looks funky. Does anything look funky to all of you? If it does, I hope you tell me. It's not the cleanest board in the world, but we're used to that by now. Nothing looks too off kilter here. And 3.9 kiloohms is hardly something to phone home about when it comes to a short to ground on PP3V42. When you're talking about a 3.42 volt line with 3 or 4 kiloohms to ground, I mean, you're never going to find a short by injecting voltage. Never. You're in the kiloohms. Why are you producing less than you're supposed to? A little curious what the donor board here reads. On my donor board, PP3V42 is 11 kiloohms and going down. So on this board, it probably would have continued going up. That's not what my issue is. So here we're going to do what I call a Hail Mary. I'm going to replace the PP3V42_G3 hot regulator with no clear-cut reason for doing so. This is what's called a Hail Mary. Let's see if it does anything. First thing I want to do, actually, before I even replace anything, I want to see what heat does. I'm going to heat up everything in this area. I want to see if it changes the behavior. Nah, that resistor's in trace just fine. Interesting, we get a different reaction. After heating everything up, it's taking 500 milliamps. This is going to be a difficult one. Difficult one indeed. Yeah, we got a green light in the charger, and it's turning on. Oh, that's very strange. Okay, so what we're going to do is I'm going to replace the caps on output in that area. I do wonder if they were not doing their job and not storing things properly. Yeah, so C7099, C7098. Remember the C7771 circuit, or C9560, where voltage goes out and down on output. Now granted, those were tantalum systems. These are ceramics. They typically don't have that issue. So it could have just been some funky solder joint somewhere. But still, don't want to risk anything. And replacing things is not going to cost us much money. Yeah, and this cap on its left, it has had a little mark on it. That was kind of strange to me. And you never really know exactly what it is. You're not always going to know exactly what it is. You just got to be close enough. The genius part seeing this and saying just buy a new computer, that wouldn't be a far off estimate from what might actually happen there. Now that's not soldered into place yet, and that's fine. I want to minimize the amount of heat I apply there. I apply just enough heat to get it kind of stuck in place, because I'm going to have to use a decent amount of heat to get my chip into place. And that is where I am going to allow the heat to not just heat the chip into place, but also put those caps in their place as well. Or not. Okay, it's being a mofo. One moment. Don't you hate it when the board acts like a mofo? That's fine, though. It can protest all it wants. It can protest all it wants. It's not going to get anywhere. No, little capacitor. You're going where I tell you to go, little capacitor. Now the bottom pads are both going to the same place, so it doesn't matter if they're touching. That whole area right there all goes to the same place. This, see, it's all tied together. So they can touch. I won't be mad at them for touching. I will be mad at that other chip for being crooked, though. We can do better than that. Now, this is not going to be one of those boards where I just test it and I call it a day. There's actually a fairly good chance of this not working tomorrow. Anytime something works when you heat something up, it's very difficult to tell which component you heated up. Did I heat this? Was I heating this? Was I heating this? I made an educated guess that it was these two based on personal experience with many other machines. However, that doesn't mean that that was the issue. So even if it works now, it may not work later. So I'd actually like to give this board a little bit more time, assuming the customer is willing to be patient. I'd like to make sure that this works tomorrow. Cool it off. Make sure it works the day after that. Do a stress test, get it nice and hot, make sure it doesn't randomly turn off or anything like that. Just to make sure that we're 100% certain that what we did actually addressed their problem. The last thing anybody wants is something that works now and doesn't work tomorrow, right? There we go. Plug you in. You get a nice little light in the charger and a happy spinning fan. As I like to say, when humans are happy, they smile. When MacBooks are happy, their fans spin. That's it for today. And as always, I hope you learned something. I'll see you all in the next video. Bye now. And if any of you want to learn how to do any of the stuff that I talk about in this video, check the links in the description down below. We have a 100-plus page beginner's guide that goes over everything that's completely free. We have Repair.wiki, which is also completely free, and includes lots of really good troubleshooting information. And we also have an in-person class. I'll see you all in the next video. If you're interested in doing the type of work that we do in this video, repairing motherboards at component level, and you'd like to learn more for free, I'd highly suggest that you check out our YouTube channel at youtube.com/Rossman Group. When you visit the channel, you can click on Playlists, scroll down, and you'll see a playlist called MacBook Component Level Logic Board Repairs. On this playlist, you will find over 600 videos detailing how to fix MacBook motherboards. If you feel like the content in these videos is a little bit too advanced for you, or like you need to learn a little bit more electronics theory before you're able to understand what we're going over, you can scroll down in the video description and click on the beginner's guide. When you click on the beginner's guide, you'll see this 150 slide guide that goes over everything from short detection to how transistors work, to how data lines work, to how buck converters work, so that you can better understand how to do these types of repairs. If you would like more free help, you can visit Repair.wiki. On Repair.wiki, we have all of the devices listed by model and board number, along with common solutions and common problems, so that you can get an idea idea of where to look for your particular problem. If you're unsure how to fix it and you just want to pay somebody else to fix it, look no further than rossmangroup.com. On rossmangroup.com, you can find repair services as well as mail-in repair services where you can mail in your repair from anywhere and we'll take care of it for you. If you'd like some paid help with your board repair but you'd still like to do it yourself, you can check out boards.rossmangroup.com where we have expert-level technicians that will answer your questions for the low, low price of $29 a month. If you'd like to learn how to do this in an in-person classroom environment, look no further than rossmangroup.com where you can go here, scroll down, click Learn Logic Board Repair, and sign up for a paid class to learn how to fix motherboards and learn in person how to do the work that we do here on this channel. We have paid resources available, and we also have free resources available for those who'd like to learn who don't have a budget to be able to pay for an in-person class. Lastly, if you'd like to purchase any of the tools that we used in this video, you can check the video description and you will see all of the tools that we use, from microscopes to freeze spray to soldering stations to soldering tips and so on and so forth. And you can visit places like store.rossmangroup.com to purchase some of the tools we use, like the A1466 Hot Air Rework Station. That's it for today, and as always, I hope you learned something. I'll see you all in the next video. Bye now.